Section: Introduction. In this section, we delve into the realm of large language models, LLMs, and their challenges when it comes to generating accurate information. We explore how retrieval-augmented generation (RAG) systems have been developed to enhance the flexibility and extensibility of LLMs by tapping into internal data sources. However, these systems still face issues with generating text that aligns well with the provided knowledge source. Our goal is to ensure that LLMs exhibit faithfulness by producing outputs that are firmly rooted in the retrieved contexts. To tackle this challenge, we introduce RAGs, a system that uses LLMs to generate statements from question-answer pairs and assesses their faithfulness based on how well they are supported by the given context. We also explore the use of LLMs as judges to evaluate hallucinations, which require these language models to possess nuanced reasoning and disambiguation abilities. We propose Lynx 70B as a solution that surpasses existing models in detecting hallucinations while remaining open source and reproducible. By training Lynx on diverse datasets and focusing on hard-to-detect hallucinations, we aim to bridge the performance gap between closed and open source models, especially in specialized domains like finance and medicine. To evaluate the effectiveness of hallucination detection systems, we introduce HaluBench, a benchmark comprising 15K samples annotated for the presence of hallucinations across various real-world domains. Our contributions include the development of Lynx, the first open-source LLM capable of high-quality hallucination detection, and the proposal of a novel method to generate challenging hallucination examples through semantic perturbations. Furthermore, we conduct experiments to compare Lynx against both closed and open-source LLMs and RAG evaluation metrics. All our models, datasets, and experiment results are made publicly accessible on platforms like Hugging Face and GitHub for further research and development. In the realm of related work, we discuss the challenges faced by LLMs in generating accurate information and the techniques proposed to evaluate hallucinations in these models. We highlight the importance of automatic evaluation methods, such as RAGs and exam, in assessing the correctness and groundedness of LLM outputs. Additionally, we touch upon the significance of natural language inference (NLI) tasks in detecting inconsistencies in LLM outputs and the relevance of factuality evaluation in building trust in AI systems. Our focus remains on addressing the issue of hallucination detection in RAG settings, emphasizing the need for comprehensive benchmarks like HaluBench to evaluate model performance effectively. Section Summary. In this section, we introduce the concept of retrieval-augmented generation (RAG) systems that enhance large language models (LLMs) by enabling them to access internal data stores for more flexible and extensible knowledge utilization. We highlight the importance of faithfulness in RAG systems, where LLMs should produce outputs grounded in retrieved contexts to avoid generating inconsistent text. To address the challenge of hallucination detection in LLMs, we propose Lynx, an open-source model that outperforms closed-source alternatives in detecting hallucinations, especially in specialized domains like finance and medicine, by introducing a comprehensive benchmark called HaluBench. Section: Methodology. In this section, we first retrieve relevant contexts based on a query and then generate an answer using an LLM. Hallucinations can happen when the generated answers do not match the context, intrinsic hallucinations, or reality, extrinsic hallucinations. Our focus is on intrinsic hallucination evaluation because user-provided documents may conflict with external knowledge sources. Our goal with Lynx is to offer a metric for automated RAG evaluation without considering factuality assessments. We explain the training process for Lynx, a top-notch hallucination detection LLM, starting with the hallucination definition and then how we created our training and evaluation data. We also share experimental results on hallucination tasks from real-world domains. For a given question X, we define hallucination as when the LLM's answer P, X, does not align with the context C, X. Often, LLM answers do not match the retrieved context. In our definition, we do not evaluate the relevance of the context C, X, to the query X. If the answer P, X, aligns with the irrelevant context C, X, we consider it faithful. Similarly, if the answer P, X, is incorrect but consistent with the context C, X, we deem it faithful. We gathered examples from various QA datasets to create the Hallucination Evaluation Benchmark, HaluBench. This benchmark includes tasks like FinanceBench, Drop, COVID QA, PubMed QA, HaluEval, and RAG Truth. To construct examples with unfaithful answers, we used a perturbation method to generate altered versions of correct answers that introduce inconsistencies with the context, resulting in hallucinations. We ensured a balance of positive and negative labels in the final task dataset. Section Summary. In this section, we focus on evaluating intrinsic hallucinations in a RAG pipeline, where generated answers may not align with the context. We introduce Lynx as a reference-free metric for automated hallucination detection, emphasizing the importance of assessing hallucinations without factuality considerations. By constructing the HaluBench dataset from various QA datasets and generating semantically perturbed answers, we aim to provide a balanced evaluation benchmark for detecting hallucinations in generated responses. Section: Human Annotation. In this section, we conducted human annotation to ensure the quality of the generated samples by our language model, LLM, in HaluBench and to confirm that our perturber F_P indeed induced hallucinations. We randomly selected 50 examples from Drop, FinanceBench, COVID QA, and PubMed QA for manual checking by expert annotators. The annotators reviewed both the original and perturbed answers, as well as the reasoning provided for each example. The data was found to be of high quality, with a high human agreement of 0.94 across the 200 samples. Moving on to model training, we constructed a training dataset for Lynx consisting of 2,400 samples, with an additional 800 samples for validation. These samples were sourced from RAG Truth, Drop, COVID QA, and PubMed QA. For each subtask, we selected 600 examples from the training split of the source dataset, out of which 300 were perturbed to create hallucinated answers. We utilized chain of thought, COT, to enhance the zero-shot performance of LLMs. To evaluate the reasoning capabilities of our fine-tuned open-source model, we employed GPT-4o to generate reasoning for the label of each example in our training set. This reasoning was provided as part of the assistant response during the instruction tuning process. We also implemented self-instruct tuning by training two models with supervised fine-tuning using specific checkpoints on a dataset of 2,400 examples formatted for instruction tuning in a chat-based format. For evaluation, we assessed Lynx on HaluBench to evaluate its performance in hallucination detection in real-world scenarios. We compared our model with various baseline methods by prompting it to determine if the response aligned with the context, providing a binary score of pass for faithful responses and fail for hallucinated ones. Lynx 70B demonstrated the highest accuracy across all evaluation tasks, outperforming GPT-4o by nearly 1% on average. In domain-specific tasks, Lynx 70B excelled further, showing an 8.3% higher accuracy in identifying inaccurate responses in medical answers in PubMed QA compared to GPT-4o. Both Lynx 8B and Lynx 70B exhibited increased accuracy compared to the baseline Llama 3 models, with the fine-tuned 70B model achieving a 7.8% average accuracy improvement. Furthermore, Lynx surpassed GPT 3.5 Turbo by a significant margin, with a 27.6% average accuracy increase across all tasks. Lynx 70B emerged as the top-performing model with 87.4% accuracy on HaluBench, while GPT 3.5 Turbo displayed the lowest accuracy among all models evaluated, averaging 58.7% accuracy across all tasks.